This is lesson number 4 for engineering dynamics. In this tutorial we will look at polar, cylindrical and spherical coordinates. The tutorial contents includes an introduction to polar coordinates, including one example, cylindrical coordinates including one example, and spherical coordinates including one example. So let's get started. So polar coordinates. So if we take our xy axis here and we say the particle is located at a position r and an angle of theta from the x-axis, we're going to assign two unit vectors, one called u sub r and u sub theta, where u sub r acts in the direction of r and is pointing radially, and u sub theta is pointing perpendicular to r, so that is called the transverse unit vector, u sub r. And in the radial direction we say that's r, so the r direction, and in the u sub theta direction we say that's theta. Okay, so r is the radial direction defined by the unit vector u sub r, and theta is the transverse direction defined by the unit vector u sub theta. So the particle moves through a radial coordinate r extending outward from origin O. Okay, so it moves radially from origin O. The radial direction is defined with unit vector u sub r. The particle also moves in a transverse direction to the radial coordinate in an anti-clockwise direction. This is defined by the unit vector u sub theta. That is the unit vector u sub theta, and that moves in the transverse direction. And if it's moving anti-clockwise, we say that is the positive direction. So polar coordinates are useful when the motion of the particle is controlled through a radial distance and angular position. All the particle motion is being observed with radial distance and angular position measurements. Okay, so you need to be aware that this particle is capable of rotating, okay, and moving radially at the same time. Okay, so this allows for some pretty complex motion. So the angle theta is measured from an arbitrary line shown by the x-axis and is measured in degrees or radians. However, in our calculations, we should always be using radians. Okay, so calculations should always be carried out in radians. The position theta can be defined in degrees, but when we're carrying out calculations, we always work in radians. So when you're given problem sets, and let's say the angle is defined as degrees, the first thing you need to do is always convert that into radians. The vector u sub r is in the direction of increase in r when theta is held constant. Okay, so if we held theta constant, the unit vector u sub r is in the direction of increasing r. Vector u sub theta is in the direction of increasing theta when r is held constant. Note that if r is held constant, then the particle's motion is described by equations for circular motion, as discussed in the previous tutorial. Okay, so if we hold r constant, so r is not changing with time, and is only free to move in the u sub theta direction, or in the theta direction, then it will follow a circular motion. If theta is held constant, okay, so if this angle here, theta, is held constant, the particle's motion is described by the equations for rectilinear motion as covered in the first tutorial. Okay, so if we hold theta constant, and this particle is only constrained to move along the u sub r direction, or in the radial direction, it's just going to follow motion in a straight line. If we was to rotate theta a little bit more, so let's say r ended up here, okay, and then that was fixed, the particle would only be able to move in this straight direction like that. If r and theta are free to change, then the particle's trajectory would be a curved shape with changing radius of curvature. So if this particle is moving in the u sub theta direction, so rotating, and it's moving in the radial direction at the same time, it's going to follow a curved path, but that curved path is going to have a changing radius at each point. So the position vector r of the particle has a magnitude of the radial distance r and direction defined by unit vector r. So the magnitude of r, so r in bold here, is a vector position and it has a magnitude of r. Okay, so the magnitude of that will just be its radial length, and we have to multiply that by the unit vector u sub r to tell us that it's in the radial direction. So now we're going to talk about velocity. So to differentiate r to get v equals r dot, time derivatives of both unit vectors u sub r and u sub theta are needed. So if we want to describe what the particle's velocity is, we need to know how u sub r and u sub theta are changing in time. Okay, so if we take these two unit vectors and put them over here, so we've just zoomed in on these two unit vectors and put them there. Okay, so this is the unit vector u sub theta, and that is the unit vector u sub r. Okay, so when the particle is moving in the radial and transverse directions, the unit vectors would have rotated through an angle of d theta. Okay, so has rotated to this position, we're calling u sub r prime, and u sub theta has moved to this position here, we're calling u sub theta prime. And they both rotate through an angle of d theta. Okay, so d theta is the infinitely small change in its angle. So du sub r is going to occur in this direction, so we can approximate this with a straight line, because this is an infinitely small change in d theta. Okay, so that's du sub r, and that is in the direction positive theta. And that's du sub theta, and that is in the direction of negative r, so in the negative radial direction. So using the fact that radii u sub r and u sub theta multiplied by d theta will give du sub r and du sub theta respectively, since these are infinitesimally small changes, and the fact that these are all unit vectors, so length is unity, so the length of them is just 1, and displace the same angle d theta, we can write this equation here. So du sub r equals d theta times u sub theta. Okay, so if we want to calculate du sub r, we would do u sub r times d theta. Okay, but since u sub r and u sub theta are the same length, we can say du sub r equals d theta times u sub theta. And we can do the same thing for du sub theta, where it's going to be minus d theta times u sub r. So the minus is because it's going towards the negative radial direction here, so not forgetting the minus. So again, to calculate du sub theta, we would do u sub theta times d theta to get du sub theta. But because u sub theta and u sub r are the same length, we can say du sub theta equals minus d theta times u sub r. Okay, so if we take du sub r equals d theta times u sub theta and we put that here, I'm going to divide both sides by dt to get our time derivative. Okay, so if I divide both sides by dt, I get this. So that means I can write that like this. So u sub r dot equals theta dot times u sub theta. And I can take this expression here, so du sub theta equals minus d theta times u sub r, divide both sides by dt, and I get this, and I can rewrite that as u sub theta dot equals minus theta dot times u sub r. Okay, so if I take this expression again, so r equals r times u sub r, so that is the vector position of the particle here, and then we differentiate this with respect to time. But since r, so r here and u sub r are both changing in time, we'd have to use the product rule. Okay, so r is changing in time, so as the particle starts moving along the curve, r is going to change, and u sub r is also going to change with time, but what's actually changing is its direction. Okay, because this is a unit vector, its length is always 1, but what's changing with time is just its direction. So we use the product rule for that to differentiate that with respect to time. So to differentiate this with respect to time, we differentiate r and leave u sub r alone, and then we leave r alone and differentiate u sub r with respect to time to get this here. So that's just the product rule. And then I can rewrite that like this. Okay, so r dot equals r dot times u sub r plus r times u sub r dot. And then I can substitute u sub r dot into here to get this. Okay, so u sub r dot was this expression here. So all I did was substitute that into there to get this. Okay, so we get r dot equals r dot times u sub r plus r times theta dot times u sub theta. Okay, so that is our velocity in polar coordinates. So we can rewrite that like this. So r dot equals v, which equals r dot times u sub r plus r times theta dot times u sub theta. So there's our velocity there. So now if we want to find acceleration, we differentiate this again. So again, we use the product rule because all of these quantities in here are changing with time. So r dot is going to be changing with time because it's accelerating, and u sub r is changing with time, r is changing with time, and theta dot is also changing with time as well, and u sub theta is also changing with time. Okay, so if we differentiate that, we get this. Okay, so just apply the product rule. The product rule applied to this here would give us this, and the product rule here would give us this. Okay, so to differentiate this, all I did was differentiate r and leave everything else alone. Then I differentiated theta dot and left u sub r and r alone. And then to get this here, I differentiated u sub theta and left theta dot and r alone to get this. Okay, so again, that was just the product rule. So now I'll substitute u sub theta dot and u sub r dot. Okay, so I'll substitute that into here and here. Okay, so I'll substitute those in, and I get this. And then I can simplify this down to that. So these two here can be written as theta dot squared. And then I can bring together the like terms. So this is a term in the u sub r direction, and that is a term in the u sub r direction. So I put them together, and I've got two of these terms here. So 2 of these terms, so that's how we get the 2 there, and we've just got r times theta double dot there. So this is in the u sub theta direction, and this is in the u sub r direction. So this is acceleration in the radial direction and acceleration in the transverse direction. Okay, so now we've got our expressions for velocity and acceleration. We no longer need the expressions for the unit vectors du sub r, du sub theta, and u sub r dot and u sub theta dot. So these are all the equations that we found. So we've got r equals r times u sub r, and we've got velocity here, and we can rewrite this like this. So we can say the velocity in the radial direction is just r dot, and the velocity in the transverse direction is just r times theta dot. And we can say the acceleration in the radial direction is just r double dot minus r times theta dot squared. Okay, so that's the acceleration in the radial direction. And we can say the acceleration in the transverse direction is 2 times theta dot times r dot plus r times theta double dot. Okay, so that is the acceleration in the transverse direction. And if we want to know the magnitude of velocity of the particle, we would just apply Pythagoras to v sub r and v sub theta. And if we wanted to know the magnitude of acceleration, we would apply Pythagoras to a sub r and a sub theta. And note, we can also write a sub theta like this. So a sub theta here can also be written like that. That might come in useful at a later stage. So let's verify this. So the chain rule and product rule are used. Okay, so I've got 2 functions here that are varying with time. So r is changing with time and theta dot is also changing with time. Okay, so I need to apply the product rule. So first I'll differentiate r squared to get r dot times 2r and leave theta dot alone. And then I'll differentiate theta dot to get theta double dot, and I'll leave r squared alone. How we would differentiate r squared with respect to time is using the chain rule. Okay, so if I say z equals r squared, and then if I want to find dz dt, remember z is r squared, I'll do dr dt times dz dr, so that is the chain rule. I can rewrite dr dt as r dot, and dz dr, if we differentiate z with respect to r, we just get 2r, and we multiply them together. And that means I can say d by dt of r squared is r dot times 2 times r. So I found the time derivative of r squared, which is r dot times 2 times r. So that's how I got this term here. And then if I distribute 1 over r into the bracket, I get r dot times 2 times theta dot plus r times theta double dot, which is exactly what we have here. Okay, so if I distribute the r, this r will cancel, and one of these r's will cancel to leave this expression here. And that is a sub theta. Okay, so these were the equations that we found. Okay, so make sure you write all of these down. So now we're going to talk about the physical meaning. We're basically going to visualize the motion of this particle in polar coordinates. Okay, so let's say we have our particle here located at this position here. Okay, so there's our unit vectors u sub r and u sub theta. Okay, and we're going to hold r constant with a constant angular velocity. Okay, so the angular velocity along that path is constant and r is being held constant. That is going to mean that v sub theta is going to be constant. Okay, so v sub theta was r times theta dot. So the angular velocity there is going to be constant. And v sub r is going to be 0 because there's no movement in the radial direction. Okay, so v sub r there is going to be 0. And a sub theta is also going to be 0. Okay, because theta dot is constant. Okay, r dot is 0, so this term is going to go. And since v sub theta is constant, theta double dot is going to be 0. Okay, so a sub theta is 0. However, a sub r is not going to be 0. So this term here, r double dot, is going to go because there's no velocity in the radial direction. So therefore there can't be any acceleration. So we're just going to get left with this. And we saw this from our previous tutorial. And this is the expression here for centripetal acceleration. So that's what happens when we hold r constant and with a constant angular velocity. So again, note that v sub theta is acting tangent to the path, and a sub r is acting along the radial direction, so towards the center. Okay, so as that rotates around, it's going to stay in that same configuration. Okay, so now we're going to hold r constant with a changing angular velocity. So now the angular velocity is changing with time, so that means we're going to have this term a sub theta here. And again, v sub theta acts in the tangential direction, and a sub r acts in the radial direction down here. And we also have a, where a is the magnitude of a sub theta and a sub r. So to find a, we just apply Pythagoras to a sub r and a sub theta. V sub theta is going to be changing because the angular velocity is changing along that path. A sub theta this time is going to be r times theta double dot. Okay, so if we look at a sub theta here, r dot is going to be 0, so this term is going to go, and we're just going to be left with this. So again, we saw this in the previous tutorial. And a sub r is still going to be the same, so it's going to be minus r times theta dot squared. However, this a sub r, that's going to be different at every point because v sub theta is speeding up, which means theta dot is also speeding up, which means it's increasing. So as it goes around the path, a sub r is increasing. So as that rotates around, that stays in the same configuration as shown here. So now we're going to hold theta constant with a constant negative linear velocity. Okay, so by negative we mean it's going to move in this direction here. Okay, so remember u sub r pointing radially outwards is positive, but if it's in this direction, the velocity will be negative. Okay, so we're holding theta constant. So this is no longer rotating around. So theta is being held constant, and we have a constant negative linear velocity going in this direction. So the particle can only move in this direction here, okay, along this line. Okay, so it can only move along there with a constant velocity. So if theta is fixed, v sub 0 is going to be 0, okay, because theta here is going to be 0, because theta dot will be 0. V sub r is constant, okay, so it's moving with a constant velocity along the radial line. A sub theta is going to be 0, okay, because theta dot is 0 there, and if theta dot is 0, we can't have any angular acceleration, so theta double dot there will be 0. So a sub theta is 0, and a sub r is also going to be 0 because r double dot was 0 because it was constant, because r dot is constant along this line, and theta dot is going to be 0, so a sub r is going to be 0. So all we literally have here is just velocity along this line. So now we're going to hold theta constant with a changing negative linear velocity, so it's accelerating along that line. Okay, so the velocity of that in the radial direction is going to increase. V sub theta is still going to be 0. V sub r is changing. It's going to be different at every point. Okay, so r dot is changing along that, and a sub theta is going to be 0 because theta dot is 0, which means theta double dot is 0, and a sub r is going to be r double dot. Okay, so we've got no centripetal acceleration here because theta dot is 0, so we only have r double dot. Okay, so that's what happens when theta is held constant with a changing negative linear velocity along that radial line. So now we're going to hold v sub r and theta dot constant. Okay, so the particle is able to move along this radial line and rotate at the same time. Okay, so that would look like this. So it's rotating and moving radially at the same time. So if we do that again, but this time draw out its path. Okay, so this is the path that it took. So remember that is with v sub r and theta dot as constant. Okay, so the angular velocity is constant and the velocity along the radial line is constant. Okay, so it can do both at the same time. So v sub theta is changing tangentially. Okay, so v sub theta is changing because r is changing. So as the particle moves along the radial line, r is going to be changing. So v sub theta is changing tangentially. V sub r is still constant radially. Okay, if it's moving constantly in the radial direction, it's still going to stay constant. And v sub theta is constant tangentially because theta dot and r double dot are constant, and theta double dot there is going to be 0 because the angular velocity was constant. So we're just going to be left with this term here. Now, we know what this term is, we know what this term is, and this term. This term here is called the Coriolis acceleration. So this can only occur when there's rotation and linear movement occurring at the same time. So for example, if you're on Earth, if you're moving around on Earth, and because the Earth is rotating at the same time, you still experience an acceleration, and that's because there's rotation and linear movement happening at the same time. So that means a sub theta there is going to be constant, okay, and that is a constant Coriolis acceleration, again because v sub r and theta dot are constant. So a sub r is changing radially, so a sub r is going to be changing radially because r is changing radially, so the centripetal acceleration is changing radially because as the particle is moving radially, the radius is changing, okay, which means the centripetal acceleration here will be changing, and r double dot there is just going to be 0 because the acceleration in the radial direction is still 0 because v sub r is constant. If we have v sub r and theta dot increasing at a constant rate, so constant acceleration, that means every single term here and here, here and here are all going to be there, okay? So we're going to have an acceleration in the radial direction minus r times theta dot squared, okay, because the centripetal force is going to act in the opposite direction to r double dot, and a sub theta is going to be composed of both the Coriolis acceleration and the tangential acceleration. So let's have a look at an example. Okay, so the particle is fixed to move on the line OP. So there's a line OP. So this origin here and this point there I'm calling P. So line OP. The line OP rotates so that theta equals 2t squared radians. Simultaneously, the particle moves outwards along the OP such that r equals 6t cubed meters, where t is in seconds. Find the velocity and acceleration of the particle 0.5 minutes after the particle has started motion. Okay, so here we're given theta as a function of time, and we're given r as a function of time as well, and we're trying to find the velocity, the magnitude of velocity and acceleration of the particle 0.5 minutes after the particle has started. It started from rest. Okay, so that's telling us it started from rest. So you can see here that this particle moves along this line, is fixed to move along this line here, so that is the radial direction there, and that line also rotates, where theta there is given as a function of time, where the function is 2t squared radians. So first thing we need to do is find r dot, r double dot, theta dot, and theta double dot at t equals 30 seconds. Okay, so I'll just convert minutes there into seconds. So first I want to find theta at 30 seconds, so all I'll do is evaluate the function there at time t equals 30 seconds, put in 30 seconds there, and I get 1800 radians. So then I want to find theta dot, so I'll just differentiate theta with respect to time to get 2 times t squared. So I want to differentiate theta with respect to time, and I know theta is 2t squared. Okay, so after differentiation I get 4t, evaluate that at 30 seconds, and I get 4 times 30, which is 120 radians per second. So that is theta dot. And for theta double dot, we differentiate theta dot. Okay, so theta dot was 4t, so I differentiate that with respect to time to get 4, so that I was going to be left with 4 radians per second squared. So now to find r, I'll take my function there for r, which is 6t cubed, evaluate that at time t equals 30 seconds. Okay, I get 162,000 meters. Now I want to find r dot, so I differentiate 6t cubed with respect to time, and I get 18t squared. Evaluate that at t equals 30 seconds. I get 18 times 30 squared, which will give me 16,200 meters per second. So then to find r double dot, I differentiate 18t squared to get 36t, and then evaluate that at time t equals 30 seconds, and I get 1080 meters per second squared. So now I found r dot, r double dot, theta dot, and theta double dot. So now I can find the velocity, okay, using this equation here. So I just took that equation there, and now I want to substitute my values in. So substitute r dot, substitute r, and theta dot to get this. So I just substituted r dot, r, and theta dot to get this. So I end up with that, and then I want to apply Pythagoras over here to get my magnitude, and I get this number here, and that is the magnitude of my velocity at time t equals 30 seconds. So now I want to find acceleration, so I'll take this term here and I'll put it down here, and then again I'll substitute all my numbers in. So I'll substitute r double dot over here, substitute r again, theta dot there, r dot, r, and theta double dot. So I'll substitute all those values in, and I get this, simplify that down, and then apply Pythagoras to that. Okay, so I'm just applying Pythagoras here, and I get this for my acceleration. We're now going to look at cylindrical coordinates, and then we'll look at another example for cylindrical coordinates. Okay, so the cylindrical coordinate system is basically the same as the polar coordinate system, where the only difference is that the particle can move in the z or k direction defined by the unit vector u sub z. Okay, so if we look on the xy plane here, okay, so there's the x-axis there and the y-axis. If we look on the xy plane, we still have our polar coordinate system where we have u sub theta there, which is acting in the transverse direction in the xy plane, and we have u sub r, which is again pointing radially outwards on the xy plane. And we also have another unit vector that's perpendicular to u sub theta and u sub r. Okay, so that is u sub z, which is acting in the u sub z direction. So this unit vector here is parallel to the z-axis here. So we still have r and we still have theta there measured from the x-axis, and we have a new position called r sub p, which is the position of the particle there in cylindrical coordinates. Okay, so you can see the particle there is moving in the u sub z direction. Okay, so it's moving vertically down. And we've got movement in the u sub theta direction. Okay, so that is movement in the u sub theta direction. And we've also got movement in the u sub r direction as well. Okay, so we define the position there, r sub p, as r times u sub r plus z times u sub z. Okay, so the position of p there is r, which is in the u sub r direction, and z, which is in the u sub z direction there. So there's our length there, z. And the velocity is just going to be the same as before, same as polar coordinates, but with z dot, which is acting in the u sub z direction. Same as we can say v sub r equals r dot, v sub theta equals r times theta dot, so we've already seen these two. But now we're saying v sub z, so the velocity in the u sub z direction is going to be z dot. So that is a time rate of change of the z distance. And acceleration is the same as before, so same as in polar coordinates there, in the u sub r and u sub theta direction. But now we've got z double dot, which is the second time derivative of the length z. Okay, so that means we can say a sub r equals r double dot minus r times theta dot squared, and a sub theta equals 2 times theta dot times r dot plus r times theta double dot. Okay, and the acceleration in the z direction is going to be z double dot. So if we want to find the magnitude of velocity, we apply Pythagoras to v sub r, v sub theta, and v sub z. So this gives us the magnitude of velocity in cylindrical coordinates, and this is the magnitude of a, so Pythagoras of a sub r, and a sub theta, and a sub z. So that should be an a. So that is the magnitude of acceleration in cylindrical coordinates. So we do Pythagoras of a sub r, a sub theta, and a sub z. And again we can say a sub theta is 1 over r times d by dt of r squared times theta dot. Okay, so we can still write this for a sub theta. So make sure you write all of this down, as we will be using this later on. So the reason it's called cylindrical coordinates is because if that particle was moving in the ur, u theta, and uz direction, and we was to trace out its path, it would create a cylindrical shape like this. So when it moves in the uz direction, it's going to change the height of that cylinder, and if it was moving in the u sub r direction, it's going to change the radius of that cylinder. Okay, so let's have a look at an example. Okay, so the particle begins motion from point P with a velocity u equals 10 meters per second and descends in the yz plane at the constant angle beta equals 25 degrees with an acceleration a equals 4 meters per second squared. Find the velocity of the particle in cylindrical coordinate components 15 seconds after it begins motion, and find theta dot, r dot, and z dot at this instant. Okay, so we are told that this particle is moving in the yz plane. So there's y there, and there's z, so it's moving in that plane. But it's a distance along the x-axis of 1,500 meters, so from point O to where it is now, from where it started from. And we're told its velocity and its acceleration in this direction here, and we are trying to find the velocity in cylindrical coordinates, and we're trying to find theta dot, r dot, and z dot at the instant 15 seconds. Okay, so first we're going to find the distance the particle moves in the xy plane 15 seconds after the particle passes the point P. Okay, so we're trying to find the distance in the xy plane. First we're going to find the velocity after 15 seconds. So the velocity is going to be u plus at. So we saw this from rectilinear motion. I've just renamed v sub 0 as u. So I put my numbers in and I get v equals 70 meters per second. So now we're going to find the distance. So the distance is going to be s minus s sub 0. So s sub 0 is our initial position, and that's going to be equal to ut plus half at squared. Put our numbers in and we get s equals 1,275 meters. Okay, so that's going to be that distance there. So now we're going to find distance in the y direction. So I'm going to call that y prime. Okay, and that's going to be 1,275 meters times cos beta. Okay, so we're trying to find this distance here. So to find that, we just apply trigonometry, where this is the adjacent and s there is the hypotenuse. So if I put my numbers in, I get 1,155.5 meters. Okay, so that's going to be y prime here. And then I can find the angle theta by treating this as the opposite to theta here. And we know this side here is 1,500 meters. So that's just trigonometry. So theta equals inverse tan of y prime over 1,500 meters. And that will give us 37.6 degrees. Okay, so remember y prime was 1,155.5 meters. Okay, so apply Pythagoras to y prime and this length here to get r. Okay, that's going to give me 1,893.46 meters. Okay, so now I know y prime, r, and theta. So now we can find the velocity in the xy plane. So the velocity in the xy plane, so v sub y, is going to be the velocity going in this direction here. So we're finding the component of this velocity, okay, in the y direction, okay, so this component of its velocity on the xy plane. So it's going to be v sub xy equals v times cos 25 degrees. So if I substitute my numbers in, I get vxy equals 63.4 meters per second. So that is my velocity in the xy plane here. So if I look on the xy plane, okay, so if I look down on it, I'm going to see this view here. So there's our y-axis there, which is here, and our x-axis, which is here. Okay, so I'm looking down on it. So u sub r is going to be acting in the direction of r, and u sub theta is going to be acting perpendicular to that, because as the particle starts moving, okay, so as it starts moving on the zy plane, r is going to start changing, and r is going to start rotating into that direction there. Okay, so it's going to move in this direction. So v sub r is acting in this direction, and v sub theta is acting in this direction. And I knew the velocity on the xy plane is straight ahead. Okay, so that is the velocity on the xy plane, which is in that direction there. Okay, and we already found that here. So if I just apply trigonometry now, so v sub r is going to equal to r dot, which is v sub xy times sine theta. Okay, so I'm trying to find v sub r. Okay, so v sub r is, I can imagine that's here. So to get that, I apply trigonometry, and then substitute my numbers in, and I get r dot equals 38.68 meters per second. Okay, so we found r dot. So I know that v sub theta equals r times theta dot, which is also equal to v sub xy times cos theta. Okay, so v sub xy here has a component in the u sub theta direction, which is v sub theta. So that means I can say r times theta dot equals v sub xy times cos theta. So put my numbers into there, I get r times theta dot equals 50.23 meters per second, and then rearrange that for theta dot, I get this, then substitute r into there to get this here. Okay, continuing on, I get theta dot equals 0.027 radians per second, and I'm going to store that here. Now to find z dot, I'll just do v sub z equals z dot, because these two are equal, and that's going to equal v times sine beta. So I'm just finding the component of v at 15 seconds in the vertical direction, so in the u sub z direction here. So that's just going to be v times sine beta. Okay, so that's going to be the velocity in this direction. Okay, so I put in v, which was 70 meters per second at 15 seconds. I know beta is 25 degrees. Put that into my calculator, and I get z dot equals 29.58 meters per second. Okay, so that's my answer for z dot. I got theta dot there, and I got r dot there. Okay, so that answers the second part of the question. But if I want to find velocity, all I do is apply Pythagoras to z dot, r dot, and v sub theta. And to get v sub theta, you just do theta dot multiplied by r, which will give you v sub theta, which is 51.12 meters per second. So to find the magnitude of velocity, I just apply Pythagoras to z dot, r dot, and v sub theta. Now that we've looked at polar coordinates and cylindrical coordinates, we're now going to look at spherical coordinates, and we will also include an example for that as well. Okay, so what I have here is the spherical coordinate system. Okay, so the particle motion in spherical coordinates moves in three directions defined by three unit vectors called u sub r, u sub theta, and u sub phi. Okay, this is used where the particle position is defined by radial distance and two angles, phi and theta. Okay, so there's the angle phi there. That is measured from the z-axis up to this position r, and this is theta here, so it's the angle between the projection of r on the xy plane. And we've also got the three unit vectors you will see in just a moment. So okay, so that is movement in u sub phi direction, and that is in the direction of u sub phi over here, so this unit vector. And we've got u sub r there, which is in the direction of r. And we've also got movement in the u sub theta direction. So when theta is increasing, that would be in the direction of u sub theta. Okay, so that is movement in the u sub theta direction. Okay, so you can see theta's increased and phi has stayed as it was. Okay, so that was movement in the u sub theta direction. And we've also got movement in the u sub r direction here. Okay, so that is movement in the u sub r direction. The velocity of the particle in the u sub r direction is just going to be r dot. So that is the time rate of change of the length of r. And the velocity in the v sub theta direction is just the angular velocity theta dot multiplied by r times sine phi. So r times sine phi is going to be this distance here. So it would give us this distance. So that length multiplied by theta dot will give us the velocity in the v sub theta direction. The velocity in the u sub phi direction is just going to be this distance here, r, multiplied by phi dot. So all this is just radius times the angular velocity, theta dot, to get v sub theta. And to get v sub phi, you just do this radius here, which is r, multiplied by phi dot. Okay, so we're just going to put them there. So because of the added geometry, a more rigorous derivation of velocity is required in order to obtain time derivatives of the unit vectors and an expression for acceleration. So we need to find an expression for acceleration in the u sub phi direction, u sub r, and u sub theta direction. So because of the geometry, this can be quite complicated. Okay, so if we imagine this particle moving in the u sub phi, u sub r, and u sub theta direction, and we trace out its path. Okay, so if we did that, we'd end up with a spherical shape. Okay, so this trace here, this would be in the u sub theta direction, and this trace here would be in the u sub phi direction. So the radius of the sphere will change with movement in the u sub r direction. So this is why it's called spherical coordinates. Okay, so all I did here was just move these three unit vectors to the origin. Okay, because now we need to find our expression for the time rate of change of these unit vectors. Okay, so all I did was just move them from the particle down to the origin, or you can just see it as making phi 0 and moving the particle down to the origin. Note that all three unit vectors always remain perpendicular to each other. Okay, so u sub r is perpendicular to u sub phi, and u sub r is also perpendicular to u sub theta, and u sub phi is also perpendicular to u sub theta. Okay, so these three always remain perpendicular to each other. That never changes. If we have a look here, so if there's movement in the u sub theta direction, that means there's going to be an angle theta. So the unit vector u sub theta is fixed to only be able to rotate about the z-axis. Okay, so u sub theta can rotate about the z-axis. Consequently, u sub phi also rotates about the z-axis because, again, they remain perpendicular to each other. So these two angles here and here are going to be the same. However, just because u sub phi has moved an angle of theta, u sub phi is still going to be 0. Okay, so the angle phi is 0. Okay, even though that has still rotated about the z-axis, the angle phi is 0. Okay, so if we bring that back, the unit vector u sub phi is fixed to only be able to rotate about u sub theta axis. So u sub phi rotates about the u sub theta axis. Okay, so it doesn't just rotate about the y-axis. When u sub theta changes, so when that changes, this is also going to move with it like we just saw. When that then changes at the same time, it's fixed to just be able to rotate about u sub theta. So that's rotating about u sub theta. So the unit vector u sub r can rotate about both z and u sub phi axis at the same time. Okay, so u sub r here, that has just rotated about u sub theta. Okay, and then if we move u sub theta again, then u sub r has also just rotated about the z-axis at the same time. So the unit vector u sub r can rotate about both z and u sub theta axis at the same time. You can see here that u sub phi is rotating about u sub theta. Okay, so no matter where u sub theta has rotated to, u sub phi is going to go along with it and it be constrained to rotate about u sub theta. Another important point to note is that u sub theta only rotates on the xy plane. Okay, so it wouldn't move below the xy plane, it always stays on that plane. Okay, so if we imagine now we draw a projection of u sub r onto the xy plane and we call that distance there r. Okay, so all r is the projection of u sub r onto the xy plane. If we draw in our three unit vectors I, j and k, okay, like we've seen before, so the reason I've put these now is just because I want to take apart the components of u sub r, u sub theta and u sub phi and be able to define the components of each in terms of I, j and k. If I take this triangle here, okay, and put it there, so I've just drawn it upside down, and that is the angle phi, so remember the angle phi was between the z and u sub r axis, okay, so there's the z-axis and there's the u sub r unit vector, and the angle between them was phi, which I've drawn in here. And this triangle here was constructed out of the y distance there and the x distance here and the projection r, and the angle between the projection r and the x-axis was theta. Okay, so that's what I've drawn in here. And I can also say that r is equal to u sub r times sine phi. So u sub r times sine phi would be this length here. So that is the projection. So that length and this length here are equal, even though it doesn't look it in the diagram, but they are both equal because this is the projection r here and that is the projection r there as well. So I can say r equals u sub r times sine theta, this length here, just using trigonometry. And then I can say x equals r times cos theta, so I got that from here. And so I can substitute r into there to get x equals u sub r times cos theta times sine phi. And then I can say from this triangle, y equals r times sine theta. Okay, so this length here, that is equal to r times sine theta. And again, I can substitute r into there from here. So I substituted r into here to get y equals u sub r times sine phi times sine theta. And I can also say z equals u sub r times cos phi. Okay, so that's this side here. So again, just applying trigonometry there. Okay, so I can take x, y, and z and write them like this. So I've got u sub r equals u sub r times cos theta times sine phi, and that is in the I direction. So all I did was multiply this length here by the unit vector I to show us that that is in the I direction. And then I took y here, put it there to get u sub r times sine phi times sine theta multiplied by the unit vector j, which is telling us that is in the j direction, and u sub r times cos phi, so this length here, multiply that by the unit vector k to tell us that that is in the k direction. Okay, so that is for u sub r. Okay, so I'm going to do the same thing again, but this time for the unit vector u sub phi. Okay, so I can construct these triangles. So again, there's r there, and here, and r here as well. So this triangle is constructed out of the y distance there, and the x distance here. Okay, and the angle between r and the x-axis is theta. And then this triangle here was constructed from r and the distance z here. So remember, this is coming out onto the xy plane and also out of u sub phi. And the angle between r and u sub phi was phi. Okay, so this angle here is this angle there. So again, I can say r equals u sub phi times cos phi. Okay, so that's this length here, so r, and I've also put it here as well, so r equals u sub phi times cos phi. And I can say from this triangle, x equals r times cos theta, so this length here. Substitute r into there to get this expression for x, for this length here, x. And I can say y equals r times sine theta, so this length here. And substitute r into there again from there to get this. That is this length here, and not forgetting that minus to tell us that it's in the minus direction. So again, I can write that like this. So I've got this much of u sub phi in the I direction, this much of u sub phi in the j direction, and this much of u sub phi in the k direction. Okay, so now I'm going to take apart the components for u sub theta. So I'm going to construct this triangle. So this is just constructed out of the x distance here and the y distance there. Okay, so that's this distance here. There's u sub theta there and the u sub theta there, and the angle between the y-axis and u sub theta was theta. Okay, so that's here. So I can say x equals minus u sub theta times sine theta, and it's minus because it's on the minus side. And I can say y equals u sub theta times cos theta, so that is this length here. Okay, so I'll write that in vector form again. So u sub theta is this much of u sub theta in the negative I direction, plus u sub theta times cos theta in the positive j direction. Here are the three expressions that I found, and out of this I can also construct some useful equations that will come in handy later on. So I can take all the terms in the I direction and put them together like this. So u sub r times cos theta times sine phi is in the I direction. I know that because it's multiplied by the unit vector I, so I put that into there. Same thing with this term, that's in the I direction. Same thing with this term, and that is in the minus I direction. I do the same thing with the terms with a j unit vector in them to get this expression here, and the same thing with the k unit vectors. So that is this term and this term. Okay, so remember we had two angular velocities, so theta dot and phi dot. So we need to take those two angular velocities and write them in a vector form. Okay, so the way we do that would be like this. So omega is going to be phi dot multiplied by the unit vector u sub theta plus theta dot multiplied by the unit vector k. Okay, so the way we write angular velocity in vector form is multiplying the magnitude of the angular velocity by the axis it's rotating around. So remember, phi dot was rotating about the u sub theta axis, and theta dot is rotating about the k axis. So since I know the unit vector here, k, I can substitute this expression here into k to get this, and then I can just rewrite the order as well. Okay, so all I did there was just move this term here instead. So that was my expression for the total angular velocity. So if I want to evaluate the cross products, okay, so if I look at the cross products here, if I do the cross product between u sub theta and u sub phi, I get minus u sub r, and the cross product between u sub phi and u sub r will give me minus u sub theta, and the cross product between u sub theta and u sub r will give me u sub theta. Okay, so the order changes the sign. Okay, so here I've got u sub theta crossed with u sub r, which gives me a positive u sub phi, and u sub r crossed with u sub theta will give me negative u sub phi. So these are all the combinations I have. So the cross product between two vectors that are the same, okay, so u sub r crossed with u sub r will give 0, and u sub theta crossed with u sub theta will give 0, and u sub phi crossed with u sub phi will give 0. Okay, so these are all the cross products that we have. So u sub r dot is going to be omega crossed with u sub r. This is like saying velocity equals the angular velocity multiplied by the radial distance, okay? But because these are vectors, I have to take the cross product to get the time derivative of u sub r. So if I substitute omega into here, I get this. So I'm doing omega, so this is omega crossed with u sub r. Okay, so if I expand those brackets, so I'm taking the cross product between u sub r here and u sub r, and u sub phi and u sub r, and u sub theta and u sub r. Okay, so if I evaluate that, I get this. Okay, so all I did was just expand the bracket and take the cross product with each unit vector inside the bracket. So the cross product between u sub r and u sub r will give 0. The cross product between u sub phi and u sub r will give u sub theta. And the cross product between u sub theta and u sub r will give positive u sub phi, as shown here. Okay, so now we'll do the same thing for u sub theta dot. So the cross product between the total angular velocity and the unit vector u sub theta. Okay, so again I'll substitute omega into there from here, and I'm crossing that with u sub theta. Okay, so again expand it out. So the cross product between u sub r and u sub theta, okay, so u sub r and u sub theta is going to give me negative u sub phi, so that's what I get here. And the cross product between u sub phi and u sub theta, okay, is going to give me positive u sub r, but because I've got a negative there, that stays. And the cross product between u sub theta and u sub theta will give me 0, so this term is going to go. Okay, so let's do the last one. So for u sub phi, so I'll do the cross product between omega, the total angular velocity, and u sub phi. Substitute omega in again, expand the bracket again, and the cross product between u sub r and u sub phi give me u sub theta. Okay, so I get u sub theta here. And the cross product between u sub phi and u sub phi will be 0. And the cross product between u sub theta and u sub phi will give me u sub r. So I can just get rid of these external brackets there. And I can store this expression over here. So these are the three time derivatives of our unit vectors u sub r, u sub theta, and u sub phi. Okay, so I'll take my expression I had for u sub r earlier on. Okay, so now what I'm going to do is rewrite that like this. So instead of saying I've got a unit vector here, u sub r, I'm actually just going to replace that with the radial distance there, because they're in the same direction. The only thing that's different is going to be their magnitude. Okay, so I can rewrite that like this. So all I did is just replace u sub r with r. And then I can differentiate r with respect to time using the product rule and chain rule in the I direction. Okay, so I'm going to differentiate this term here in the I direction with respect to time. Okay, and that's going to give me this. First I'll differentiate r to get r dot there, and I'll leave everything else alone. And then I'll differentiate cos theta there with respect to time to get minus sine theta. Okay, and I get a theta dot pop up because of the chain rule. And then I'll differentiate sine phi there to get cos phi here, and again a phi dot will pop up because of the chain rule. And then I'll differentiate r with respect to time using the product rule and chain rule again in the j direction. So this time I'm differentiating this term with respect to time, okay, using the product rule and chain rule. So same technique I did before. And once I apply that, I'll then get this expression here. Okay, do the same thing again for the k direction, and I get this. These are the three time derivatives we had for r dot. So I've just put them into a long equation here like this. I would write this in a matrix format, however, I'm not too sure if you're familiar with that, so I'm just going to stick to this format here. Okay, so all of these terms are in the I direction, all of these terms are in the J direction, and all of these terms are in the K direction. Okay, so that is r dot, so the velocity of the particle. So if you remember these equations for earlier on that we got for I, J, and K, I'm now going to use these to simplify things down a bit. Okay, so if I look at these terms here, I can see that they're all here as well. Okay, so I've got cos theta, sine phi, cos theta, sine phi, sine phi, sine theta, sine phi, sine theta there, and I've got a cos phi there. Okay, so I can take these terms here and write them out down here. Okay, so again, notice that these three are here, and then I can take those three and write them out like this. So this term here is going to be in the I direction, this term is in the J direction, and this term is in the K direction. And then I can rewrite this, so I equals u sub r times cos theta sine phi, as u sub r equals cos theta times sine phi times I. And so instead of saying I have this much of u sub r in the I direction, I'm now saying I've got this much of I in the u sub r direction. They mean the same thing, but they are just reciprocals of each other. Okay, so I can do the same thing for the J term, same thing for the K term. Okay, and then I can take these here and rewrite them down there to get an expression for u sub r in terms of I, J, and K. And then if I factor out r dot from each term, I'll get this. Okay, so all I did was factor out r dot from each term. And then I'm going to substitute u sub r into here, because this whole term here is the same as this term. So if I do that, I'll get r dot equals r dot times u sub r. And that is our velocity in the u sub r direction. So this is what we got earlier on, but now we've just done a thorough derivation of that. Okay, so I'll put that to one side. So again, if you notice, these three terms here are also present here as well. So if I take each term and write them down here, okay, so this term down here was in the I direction, this term in the J direction, and this term in the K direction. Okay, so again, notice that these terms here are the same as these here. Take these terms and put them down here. So this term here was in the I direction, this term was in the J direction, and this term was in the K direction. I can then rewrite these again like this. So instead of saying I've got this much of u sub phi in the I direction, I'm now saying I've got this much of I in the u sub phi direction. Okay, and the same thing was applied to each term. But then I can take these again and write u sub phi like this by getting my expression for u sub phi in terms of I, J, and K. And then if I factor out an r times phi dot from each term, okay, so I've got an r times phi dot here, there, and there, factor them out to get this. And now I'm going to substitute u sub phi into here, because it's the same as this, and I'll get this. So r dot equals r times phi dot times u sub phi. Okay, so this is the velocity in the u sub phi direction. And again, this is what we had earlier on as well. So I'll put that to one side. So these final two terms here, sine theta and cos theta. Okay, so I've got sine theta there and cos theta there. Okay, so I can do something with these terms here. So again, if I take these and write them out like this, how much of u sub phi is in the I direction? This time I'm saying how much of I is in the u sub phi direction. So just rewrite that like this. And then I can rewrite u sub phi in terms of I and j. And then if I take these terms down here, write them down here. So I've got r dot equals minus theta dot times sine phi plus r times theta dot times sine phi times cos theta. Okay, so this term was in the I direction here, and this term was in the j direction. Okay, so factor out an r times theta dot times sine phi because they're in each term. So now I'm going to substitute u sub theta into here. So I'll take those three there. Okay, so I can write r dot in its full vector form as r dot in the u sub r direction, r times phi dot in the u sub phi direction, and r times theta dot times sine phi in the u sub theta direction. Okay, so that is my particle's velocity. So to get acceleration now, we take our velocity in the u sub r direction, we differentiate r dot with respect to time using the product rule in the u sub r direction. So apply the product rule to that to get this, and then substitute our time derivative for u sub r from here into here to get that, and then distribute that r dot to get this expression for acceleration. Okay, so you can see acceleration here is in terms of u sub r, u sub theta, and u sub phi. But we started off with the velocity in the u sub r direction. So this is just one part of it. So next we're going to have to differentiate this with respect to time and this with respect to time as well. Okay, so let's do that. Okay, so there's my velocity in the u sub phi direction. So differentiate that with respect to time. I get this. Okay, so again, applying the product rule. And then I can substitute my time derivative for u sub phi from here. Substitute that in to get this. Distribute r times phi dot to get that. And these two can be written as phi dot squared, like that. Okay, so I'm going to put that up here. And then I'm going to take this term here, differentiate that with respect to time. Okay, so differentiate with respect to time. Using the product rule, I get this. Okay, so product rule and chain rules used here. And then I'm going to substitute my time derivative for u sub theta, which was here. So substitute that in, and I get that rather long expression. So I'm going to expand this term to get that, and then I can rewrite that like this. Again, I've got theta dot times theta dot, which I can write as theta dot squared down here. And I've got theta dot times sine phi and theta dot times sine phi, so I can write that as theta dot squared times sine squared phi. And now what I'm going to do is collect all my terms in the u sub r direction. Okay, so this term here is in the u sub r direction, that's in the u sub r direction, and so is this term here. Okay, so I'm going to put them together. Okay, and then factor out u sub r from each term. Okay, so all of this is multiplied by the unit vector u sub r. And then I'm going to collect all my terms in the u sub phi direction. Okay, so that's in the u sub phi direction, so is that, and so is this. Okay, so I can put them together. And then I can rewrite that like this, because I've got two of these terms here. So r dot times phi dot, r dot and phi dot there. So I can just put a 2 there for those two. And then I can factor out u sub phi from each term to get this. So u sub phi multiplied by all of that. So leave them to one side. And then I'm going to collect all my terms in the u sub theta direction. Okay, so that's basically everything left. So this term, that term, this term, and that term there. Okay, so put them all down here. I can rewrite that like this because I've got 2 of this term here, so r dot times theta dot times sine phi, so I'll put 2 for them. Okay, so that was our expression there for velocity. Okay, so r dot equals r dot times u sub r plus r times phi dot times u sub phi plus r times theta dot times sine phi times u sub theta. Okay, so this was our expression here for velocity. So we can say that the velocity in the radial direction equals r dot, okay, from here. And we can say the velocity in the phi direction is r times phi dot, and the velocity in the theta direction. And for acceleration, I can then take these terms here and write it out fully here. So this is the acceleration in the u sub r direction, acceleration in the u sub phi direction, and acceleration in the u sub theta direction. So I can say a sub r, so the acceleration in the radial direction is r double dot minus r times phi dot squared minus r times theta dot squared times sine squared phi. Okay, so that is acceleration in the radial direction. And I can say the acceleration in the phi direction is 2 times r dot times phi dot plus r times phi double dot minus r times theta dot squared times sine phi times cos phi. So this is acceleration in the phi direction. And the acceleration in the theta direction I can say is 2 times r dot times phi dot times sine phi plus 2 times r times phi dot times theta dot times cos phi plus r times theta double dot times sine phi. Okay, so these are the expressions I have for acceleration in spherical coordinates. Okay, so if you remember this expression from earlier on, we said a sub theta in polar coordinates can be written like this. So a sub theta equals 2 times theta dot times r dot plus r times theta double dot equals 1 over r times d by dt of r squared times theta dot. So we have something similar here. I just rewritten this term like this, okay, using this identity, because I've got 2 there, r dot, phi dot, theta dot there. So these not match, and using this term as well. So r, phi double dot, theta double dot. So I'm just using this identity to rewrite this term like this. So I can apply this identity here for this expression. Okay, so first I'm going to factor out sine phi. Okay, so I've got sine phi for this term and this term. I can then take this and then rewrite just that bit using this identity. Okay, so that becomes this. Okay, so sine phi over r times d by dt of r squared times theta dot plus 2 times r times phi dot times theta dot times cos phi. Okay, so what I did was just rewrite this term using this identity. So these are our final equations for velocity and acceleration in spherical coordinates. Okay, so if you're not already familiar with these, I would jot these down now, okay, because next we are going to look at an example. Okay, so let's do our example for spherical coordinates. So we're looking at the same sort of example, but the question is slightly different. Okay, so the particle begins motion from point P down here with velocity u equals 10 meters per second. So that is the velocity it had at this point P, and ascends the YZ plane. So again, there's the Z axis, there's the Y axis. So the particle is moving in the ZY plane at the constant angle beta equals 25 degrees. So the angle beta here is the angle between the path the particle has taken and this line here, which lies on the XY plane and is parallel to Y. So with a constant angle beta equals 25 degrees, with an acceleration of a equals 4 meters per second squared, find the velocity of the particle in spherical coordinate components 15 seconds after it begins motion, and find theta dot, phi dot, and r dot at this instant. So this is what we found from the last lesson, from the last example. These still apply here. Okay, so we found what the velocity was at 15 seconds. We found theta dot, which is going to be the same in spherical coordinates as it was for cylindrical coordinates. Okay, so theta dot that we have to find here is actually the same as this. We found r, we found theta, we found z dot, we found the velocity on the xy plane, and we found r dot, which we could also call v sub r. Okay, so that is the velocity in the radial direction. So we found all this in the last example. Okay, so we need to find phi and r. Okay, because in spherical coordinates, remember phi was the angle between r and the z-axis, but we're saying phi this time is just the angle between r, small r down here. In this example, we're saying phi is the angle between here, between this line r and this line small r, just because it's easier. Normally I would define phi as the angle between z and r. Okay, so we need to find phi and big R here. So I can find z. Okay, I can find z here because I know y prime is 1155.5 meters. So I can apply trigonometry and find z. Okay, so if I substitute y prime into there, I get this, put that into my calculator, and I get z equals 538.82 meters. Okay, I can then find phi. So phi is here. So the opposite side to phi is z, and the adjacent is r. Okay, so we just found z, and we found r previously. So substitute those in, and I get phi equals 15.88 degrees. So then I can find r here by applying Pythagoras to small r and z. Okay, so that's in the zr plane, and I'm trying to find big R here. So I just apply Pythagoras using small r and z. Okay, so I found r from the previous example. We found z over here, substitute those in, and I get r equals 1968.63 meters. So I'm going to store phi and r. So there's phi that we found, and we found r. So if we look in the zr plane, so there's the z axis there, and there's the r axis here. So we're looking in that plane at the particle. Okay, so it would look like this. So we're looking head on onto that plane. So we have r here. Okay, so there's r. And we've got phi, which was between small r and big R. Okay, so phi is here. And we knew what z dot was. Okay, so z dot is going directly upwards. Okay, so we found that in the last example down here. So we know z dot is going in that direction parallel to z axis. And we know v sub r is going in the direction of small r. So it's going parallel to r in that direction. Okay, so we're drawing our unit vectors for u sub big R this time. Okay, so we've got u sub ur in that direction, and we've got u sub phi in this direction. Because as the particle starts moving along, okay, so as it starts moving along that line, r is following that, so it's getting bigger and bigger, so that means r is going to rotate in this direction. So we're trying to find v sub r, and we're trying to find v sub phi, okay? So I'm just going to draw these lines here and here, just so we complete the triangle, so we can apply trigonometry. Okay, so theta dot, as we said, it was the same in the last question. Okay, so that answers this bit. So if we say v sub r equals r dot, so big R dot, because now we're working in spherical coordinates, so I can say that's going to be v sub r times cos phi plus z dot times sine phi. Okay, so there's v sub r here. So you can imagine if phi was 0, okay, v sub r would be acting entirely in the v sub big R direction. Okay, so if this angle was 0, this velocity v sub r would be acting entirely in the u sub r direction. But we multiply that by cos phi because only a component of that is acting in the v sub big R direction over here. And this component here for z dot is acting in that direction here. So this component of z dot here is parallel to v sub big R. Okay, so that's acting in the direction of u sub r. So I'll just multiply it by sine phi to get how much of z dot is acting in the u sub big R direction. Okay, so I put my numbers in and I get v sub r equals r dot equals 37.2 plus 8.1. So this simplified to 37.2, this simplified to 8.1, and I get r dot, so big R dot is 45.3 meters per second. Okay, so I just found r dot. So we'll store that. And now I'm trying to find v sub phi. I know v sub phi previously was r times phi dot. V sub phi is over here. Okay, so v sub phi is here. And that is going to be equal to z dot times cos phi. So again, imagine if phi, this phi here was 0, z dot would be acting entirely in the u sub phi direction. Okay, but we multiply that by cos phi to get how much of z dot is acting in the u sub phi direction. And we subtract from that v sub r times sine phi, because the component of v sub r in the u sub phi direction is going in the opposite direction. So if you imagine if phi was 0, so imagine if this phi was 0, v sub r would be acting directly in the u sub r direction, and therefore will not have any component in the u sub phi direction. And if it was 90 degrees, it'd be entirely in the u sub phi direction. So to get how much of v sub r is acting in the u phi direction, we multiply that by sine phi, and the minus is because it would be acting in the opposite direction. So again, put our numbers in, and I get r times phi dot equals 28.45 minus 10.58, and then that simplifies down to 17.87 meters per second. So that means I can say v sub phi equals 17.87 meters per second, because remember, r times phi dot was equal to v sub phi. Okay, so I'm just going to keep v sub phi there. And then if I want to find phi dot, I'll just divide both sides by r to get this, substitute r in, which we found previously, and I get phi dot equals 0.0091 radians per second. So that answers the second part. So we found theta dot over here, we found phi dot over here, and we found r dot over here. So to find the velocity, okay, we just apply Pythagoras to v sub phi, r dot, and v sub theta, where v sub theta, we can obtain that by doing theta dot multiplied by r. So if we multiply these two here, we get v sub theta, which is 51.12 meters per second, and we got that in the last question. Okay, so to find the velocity, which is what the question is asking for, you just apply Pythagoras to r dot, v sub phi, and v sub theta. Okay, so if you found this video helpful and you would like to practice some more questions, then click the link in the video description, which will take you to this website here. So you can copy and paste the link directly into your search engine, or you can just click the link. So if I copy and paste the link into my search engine there, I'll be taken to this website. So this is the home page. If you click on courses, engineering dynamics, then you're taken to this page here for engineering dynamics. And you're given this formula sheet, which has all the crucial equations that we derived in this tutorial. So you've got equations for polar coordinates, cylindrical coordinates, spherical coordinates. You've also got trig identities, and you've got derivatives, and you've got integrals down at the bottom as well. Okay, so let's go back to the top. So this lesson was polar, cylindrical, and spherical coordinates. So if you click that course, you're taken to this page here. So this is the same video that we just watched, and this is a PDF which you can just view online here. You don't need to sign in or anything like that, so you can just view the questions on here and have a practice at that. Okay, so these are all the questions. So there's 16 questions in total, and the answers are shown at the bottom. Okay, down at the bottom here we have the course content. So these are just individual videos that complete each individual question on the PDF. Okay, so if you want to have a practice, have a go at these now.